Given a percentile of a PDF, we can recover key information about the parameters. We can then use that information to find more information about the PDF. For example, suppose x is exponentially distributed with 40th percentile equal to 4 log 5/3. Let's find the median of x. Since x is exponentially distributed, it will have CDF. Now we're given the 40th percentile, and that satisfies the equation. The probability that we're less than or equal to the 40th percentile is 40%. And substituting that in, we find, and that allows us to solve for lambda. And this time, for variety's sake, we won't convert everything into a decimal, but we'll try to keep things exact algebraically. And that means that I have lambda equal to 1/4. Now the median will satisfy the probability less than or equal to the median is 0.5, and so that gives us or let's consider another case. An insured vehicle has a 0.8 chance of having no accidents. If it has an accident, the damage is exponentially distributed with a mean of 3,000. Let's find the 95th percentile of the damage. So remember, concrete doesn't hurt. So if we imagine taking a large number of vehicles, then during the year, the damages in order might be something like this. Well, for most of them, 80%, that's going to be 0. And it's only for 20% that will have some amount of damage. So the 95th percentile would be in the 20% of the vehicles that were damaged. And it would be 95 minus 80, 15% in this interval. But that would be 15 out of 20, 75% of this interval. Since the damages are exponentially distributed with a mean of 3,000, we'll use the CDF for our exponential distribution. We want to find the 75th percentile of the actual damage amounts, and so solving gives us or suppose the time when students register for courses at a university has a density function that's symmetrically distributed about t equals 6.5 and is proportional to the reciprocal of t plus 1 between days 0 and 6.5. Let's find the 60th percentile of this distribution. So remember, to make the problem harder, don't sketch a graph. At the same time, graphing does take a bit of work, so remember the graph is a way to organize information. Placement is more important than accuracy. And what that means is, well, we'll show that. So that our distribution is symmetric about 6.5. So we have our 6.5, and what's to the left is looking like what's to the right. And so maybe our graph looks like this. It doesn't. But that doesn't really matter because the graph is only here to organize our information and to make our reasoning a little bit easier to figure out. So we know that the median is 6.5, and so that means the probability that we're less than or equal to 6.5 is 0.5. And remember that in the graph of a PDF, the area is the probability. And so this area to the left of 6.5 has area 0.5. Now, since we want the 60th percentile, this means we need to include an additional 10%, 0.1, to get our 60th percentile. Since the graph is symmetric, there's an area to the left of t equals 6.5 with area 0.1. And since the total area to the left is 0.5, the remaining area must be 0.4. And what that says is if we can find this point, we can find the 60th percentile. So first, let's determine our actual PDF. We have our PDF, which is proportional to, has a constant of proportionality, and we know that the median is 6.5, so that tells us the probability that we're less than or equal to 6.5 is 0.5. And so we can set up our equation where we'll factor out that constant because we can, and we find now, to keep our work from getting too cluttered, we'll just note that here's our value of C, but we'll leave it as C. So we want to solve for this 40th percentile, and so we find then substituting our value of C will give us our 40th percentile. Now here's why the graph is useful. Note that this 40th percentile is 2.49 units to the left of 6.5. But we want something that's the same distance to the right, and so that 60th percentile will be 2.49 units to the right of 6.5, or at 8.99.